Hi everybody, this is Cal with section 15.10, Change of Variables and Multiple Integrals. This is the last section of chapter 15 on multiple integration, and after this we're going to move into chapter 16 on vector fields and vector calculus. So, change of variables and multiple integrals is similar to the substitution rule from single variable calculus. And your book starts by reminding you of the substitution rule and a different way to write it than you're used to. But square one and square two are kind of interesting up here. We're going to follow a pattern here as we develop this into multiple integrals. Your book spends a little bit of time motivating change of variables over here, and then it gets into the meat of it. Your book introduces what's called a transformation. And the important parts about transformations are on the top of 1065. A transformation is just a function. It's another name for a function. And for us, it's going to be a function whose domain and range are both subsets of R2, or later on, both subsets of R3. Your book defines the image of a point under a transformation, and it defines what it means for a transformation to be one-to-one. The important thing for us, more or less, is the picture of what's going on here. So make sure you understand figure 1. This talks about the inverse transformation. We're going to make use of that. If t is 1-to-1, it has an inverse. Example 1 is going to be super important to work through. I will say, by the way, your book, we're getting to the point where it's starting to leave out details, especially algebraic details, and so you may want to work through those algebraic details to make sure you understand where everything is coming from. So work through example 1 pretty carefully. This is going to be important. And on page 1066, the book develops how we're going to handle a variable change in multiple integrals. The major idea here is that we're going to have to factor in the area change of our region under the transformation. And this is done, remember, we're splitting up our region R into little rectangles, and we're seeing what happens to those little rectangles under the transformation. I would say read through this page, try to understand where the formulas are coming from, but the meat of it is right here at the bottom where they talk about area of a parallelogram, which you probably don't remember is related to a cross product, but that's where this cross product on the next page is coming from. This shows up. So we define the Jacobian of a transformation, and this is something you definitely need to know and know how to compute. And it's the determinant of the matrix of partial derivatives. Your book continues developing the change of variables formula for multiple integrals here, and it comes up with a formula over here. Now, you can think of this formula as being similar to the substitution rule, and let me page back to the beginning of the section. In the substitution rule, we have that the integral from a to b of f of x dx is equal to the integral from c to d, where these are the bounds on u, of f of g of u. I've substituted in x equals g of u, and dx becomes g prime of u du. Now, instead of having g prime of u du in a multiple variable change, I'm paging back to where we just were. Here we've substituted x and y to x of u and v, y of u and v. And instead of a g prime of u du, we have a Jacobian of x and y with respect to u and v, du dv. So this takes the same place as that g prime of u in the substitution rule. It accounts for the change of area under your transformation. And note that this Jacobian is in absolute values. That's kind of important. Actually, scratch that. I'm talking garbage. Anyway, your book shows below here how to take the Jacobian of the transformation from rectangular to polar coordinates. And you should follow through this calculation and the answer should explain something mysterious that we've had going on when we integrate in polar coordinates. And example 2 is a really good example to work through. It follows example 1. So if you haven't worked example 1 yet, this is a good time to go back there, look at that, and then finish up with example 2. Example 3 is also really good, and I want to draw your attention to where they're getting their idea for the variable change. They have e to the x plus y over x minus y. They say, well, I don't know how to integrate that. And so they use that x plus y and x minus y as the basis for their variable change. Then their integral becomes e to the u over v, which is something they can handle. All right. Then we get into a discussion of triple integrals. It's very, very similar to double integrals. It's still the triple integral is the triple integral where I substitute my variables in, and then I multiply the Jacobian. And in example 4, we see why we have this extra little factor of rho squared sine phi when we integrate with respect to spherical coordinates. So if you follow through that, this isn't as bad as it looks, I promise. It's worth working through. Oh, so I wasn't talking garbage. The Jacobian really is in absolute values. This is an area or a volume, and we do end up getting rid of a negative when we take the Jacobian here. That ties together 15.10, and I'll be back in a moment with 16.1.